All right, so number 3, we are looking at, this is an interesting problem. Paint manufacturer made a modification to a paint to speed up its drying time. Independent, simple, random samples of 11 cans of type A, the original paint, and 9 cans of type B, the modified paint, were selected and applied to similar surfaces. The drying times in hours were recorded. The summary statistics are as follows. So there we have the summary statistics. So find a 98% confidence interval for mu1 minus mu2, the difference between the mean drying time for paint cans of type A, the mean drying time for paint cans of type B. And what does it mean? Okay, so clearly we're looking at difference of 2 means, aren't we? 2 means. Let's go back, find that stuff. There it is, 2 means. This is number 2. 2 independent means. See how I knew it was means? Because mu1 and mu2 are averages, means. Those are Greek M's. Funny looking U things, which are really Greek M's. So for mean, so we're talking means. They said mu1 minus mu2. So they want us to do a confidence interval, they said. So that means either 2-sample t-test or 2-sample t-interval. Clearly interval, because we're doing a confidence interval. So 2-sample t-interval. Let's go back to this one. We're going to do a 2-sample t-interval. 2-sample t-interval. Right? So I got that all from the mu1 minus mu2. So when you go to 2-sample t-interval on your calculator, which is way down, like down at 0. Then you got to choose data or stats. We're choosing stats. We don't have any data, but we have stats. And then basically you put in the calculator all this stuff, right? It asks you for the X1 and the S1 and everything. Just put all that right into your calculator. And then the confidence level, what'd they tell me? Where is it?
98.
Yeah, where'd it go? I can't see it. Oh, I covered it up right there, yeah. 98, yeah, so the sea level, 98%. And pooled, we always say no to, huh? Pooled is always no. You guys good with that? Remember that? Been doing that for a while. Pooled is always no. And we calculate. And so I'm getting a confidence interval that is 5.6 to 16.8. You getting that? 5.6 to 16.8? Now, they don't actually want that answer. They want what it means. What does it mean? So that's the tricky part. Now, I put that on your exam 4 notes. So let's look back. And I'll show you from the notes, and then I'll show you from logic. So if you go back, so to right here, number 4, from the exam 4 notes. Do you see it there? Meaning of a confidence interval for mu1 minus mu2. What do we do? Well, are they both negative, both positive, or one negative, one positive? What do we have? Both positive. Did you notice that as you go back to the problem here? Both are positive, huh? So what does that mean? Well, according to the notes here, all positive, 0 is not included, and it implies this stuff which ends with mu1 greater than mu2. So 0 is not included, mu1's greater than mu2. Let's go back to the problem. 0 not included, mu1 greater than mu2. Now, what is mu1? Well, it says it right here. Mu1, the difference between the mean drying time for paint cans of type A and the mean drying time for paint cans of type B. So it's A and B. Right? The paint type A is mu1, and the paint type B is mu2. So this is, oh yeah, it says right here, type A is all the, N1, S1, X1, and type B is the X2, S2, N2. It's all the 2 stuff. Right. Okay, great. So let's go on down to the answers. Could it be answer A? The confidence interval includes 0. True? No, we said right here, 0 not included, huh? 0 not included. So that's out. All right, now we're getting somewhere. How about the next one? The confidence interval includes only positive values. Is that true? Yeah, right? Positive, positive. Okay. But the next one says that too, and so does D. So we got to read on, don't we? There's more to the story than just that. What else does it say? Which suggests that the 2 population means might be equal. Does this say equal? No. One of them is greater than the other one. One of the averages is greater than the other one. Not equal. So B is out. All right, we're making headway. It's either C or D or E, none of the above. Which suggests that the mean drying times for paint A is greater than paint B. Is A greater than B? Yes. Beautiful. There it is. Uh-oh, wait a minute. This one says that too. At the mean drying time for paint A. Oh, smaller. No. So C is looking good. Answer C is it. A is greater than B. The modification seems to be effective, is it? Does that mean the paints work, the modification? Did you understand what they did? They added a chemical to one of the paints to make it dry faster. And which one had the chemical in it? Type B is the modified paint. Type B has the chemical. So B is the chemical. What did B come out? Greater or less than A? B is on the narrow side of the symbol. B's less, which is good. That means less time. That means there was strong evidence that B is less time to dry. Are we good there? B's less time. It's working. The chemical they added is working. Strong evidence for that fact. Why is this all? Let me give you the logic now. I mean, reading those words is good. But do you see why it's true? Where those words come from? Real life, you're not going to, you read a study like this, you're not going to have your exam 4 notes right there with you, right? Those are going in the trash in about 2 weeks, I'm assuming. Or you might post them on your wall. I don't know, maybe. I'm just joking around. So on a number of, so let's get to the logic. Why did I write that in exam 4? Why is that true? You really don't have to be a rocket scientist to see why that's true. It's just because that's what it means to go from positive 5.6 to positive 16.8. Right? 5.6 to 16. If I tell you I have a number and I'm 98% confident that the numbers here, we're 98% confident the numbers between positive 5.6 and positive 16.8, that means it's got to be positive. Right? If it's between 2 positive numbers, it's got to be positive. And 0's over here, and negative numbers are over there, right? So 0's not included, first off, obviously. 0's not between 2 positive numbers. Positive numbers are to the right of 0. Negative numbers are to the left of 0. So first off, we're 98% sure that it's between 2 positive numbers, it's positive. Now, what is the it, I keep saying? It. What is it? The difference. Remember, this is all about A minus B. This is all about A minus B, right? Mu1, where was it? It was, from the beginning, it was right here. It was mu1 minus mu2. That's what this is all about, huh? Group the average drying time for paint A minus the average drying time for paint B. A's time minus B's time. So we're saying when you take paint A's average drying time, subtract paint B's average drying time, you get a positive answer because it's somewhere, we're 98% sure, it's somewhere between those 2 positive numbers. So it's positive. What does that mean if you subtract 2 numbers and the answer comes out positive? Which one's bigger? Yeah, right? Yeah, that'd be something like 7 minus 2 is positive 5. You can read that, say scribble it up there in the words. But yeah, to subtract 2 things and get a positive answer, the first one's got to be bigger, doesn't it? So that means A's bigger, A's greater. See how that comes about? Real natural? That's all that's saying. If you're subtracting 2 things and getting a positive answer, the first one's got to be bigger. A's got to be bigger. That's what that means. All right, that's where that comes from. Let's move on. Well, are there questions like, why can't we just say that 76.3 minus 65.1, that's the difference in the averages, right? That's x bar 1 minus x bar 2. That's 11, what is it, 11.2? The difference is 11.2, of course. A is bigger than B. That's the same thing as A minus B. A is bigger than B by 11.2. What all this weird talk about 98% confident and we think we're pretty sure. It's for sure, right?
No.
It's not. Why not? What's going on? What are we doing here?
Probability of luck.
What's that?
Probability of luck.
Probability of
Luck.
luck?
Yeah.
Yeah. Okay. Explain to me like I know nothing about statistics. Because that's when you got something, right? When you can bring it to the man or woman on the street. You can say, here's what's going on. So what if the man or woman said, what are you doing? I can subtract those differences. The average is 11.2. The difference in average is 11.2. Of course, paint A is bigger. We just did it. The difference is A is bigger. 76 is bigger than 65. What am I, stupid? I know 76 is bigger than 65. Yes, A is bigger. It has to do with luck. What about luck specifically? What would you say?
There's a chance that, for instance, one of the tests from type B paint is actually bigger than type A, and it puts it outside of the range, or like the other way around is.
Yeah. Remember what we're trying to figure out. We're trying to decide if paint A will always do this. We only tested 11 cans. This isn't every ounce of paint A in the world. This is 11 cans of paint A and 9 cans of paint B. So I would say to that person, yes, for these 11 cans of A and 9 cans of B, for sure for these 11 and 9, 20 cans, that was the case. But the question is, what the manufacturer would want to know, could this have just been a lucky group? Maybe we just got 11 cans that happened to go longer or shorter or whatever because they were manufactured in a certain factory that made them wrong or whatever, or they got hot on the shelf or cold, or something weird happened with the paint. And so maybe there was some luck involved here. And even though, yeah, for sure with this sample A came out bigger, but maybe if we kept doing more and more cans, we'd find out A really isn't bigger, and this was just a lucky first 11. Couldn't that happen? Yeah, that could. You see, remember, we're always saying we want to know the truth of A overall, not just for the little group we looked at. Remember, that's what statistics is all about. You look at a little group and try to determine something about the whole thing. Don't you? We're looking at 11 cans of A and 9 cans of B and trying to decide overall what is the truth with Formula A and Formula B. How are they going to work over the next 10 years with thousands and thousands of paint cans? Well, we're 98% sure. In other words, there's not a very good chance of luck, huh? Because that's enough cans to make us pretty sure. We're 98% sure. Yeah, there's a 2% chance that maybe it's out of the zone and something really weird happened. But we're 98% sure. You can take that to the bank, as they say. That's pretty sure. We're 98% sure that the difference for all, in the next 10 years, between all cans of A and B will be somewhere in that zone, proving that A really is a longer formula and B is a quicker, that the chemical really is going to work over the next 10 years. That would be strong scientific, statistical evidence that the chemical formula B is really working. Does that make sense? So it's a good question. I like to clarify that every now and then. That really is the point of statistics, is that we're looking at a small sample to determine something about the overall truth. Good. All right. I hope I didn't talk that to death for you, but that's valuable. All right. Number 4. A researcher was interested in comparing the resulting pulse rates of people who exercise regularly and of those who do not exercise regularly. Independent simple random samples of 16 people who do not exercise regularly and 12 who exercise regularly were selected, and the resting pulse rates in beats per minute were recorded. There's the data. Okay, at the 0.025 stem cell test, the claim that the mean resting pulse rates of the people who do not exercise regularly is larger than the mean resting pulse rate of those who do, or do not, or whatever they said. Yeah, so if you're reading these, what if, this is what I hear typically from students. Students say, Ms. Tarrant, I can do all the homework, but when they're on the test and they're all mixed up, I just have no idea. I just read this and I just go, I don't know. We got like 10 different tests. I don't know which one. I understand that is exactly the hard part. That's why I give you all these practice exams. I want to help you with that. So what you need to do is focus on the words. Specifically, claim, Go to the word claim and see what's being claimed. And read and understand those words. The mean, so that's average, Average. So this is not a proportion problem, is it? The average resting pulse rate for those who do not exercise. So the claim is the average one for the they do not exercise regularly, is larger, greater, than mu2, those who exercise regularly. Right? Isn't that what's being said? So I got that out of the claim? Out of those words? So just keep practicing reading those words and trying to pull out what it's saying. So let's go to mu1, mu2. Where's that going to be on our exam 2 notes? Exam 4 notes? I always say 2. Yeah, it's got to be the 2-sample t-test. Exactly, 2-sample t-test? We good there? 2-sample t-test. So let's grab it, 2-sample t-test. Because we have 2 means again, 2 independent means. Where are we? Getting lost. 2 samples. Okay, so the HO is mu1 equals mu2. The H1 is mu1 is greater than mu2. It's the claim. This is weak evidence. This is strong. We go to our calculator. 2-sample t-test on our calculator. 2-sample t, and we choose either data or stats. We have stats again. We don't have any data here. Choose stats, and we get x1. Basically we get all that stuff up there, Just all that stuff. So put all that stuff in your calculator. And ours is a what? A greater test, right? Whatever H1 says, greater. And pooled is always no, as you know. Calculate. So I'm getting a p-value that's equal to 0.107. Again, pooled was no, it's always no. P is 0.107. There it is. So we didn't have to draw a conclusion or anything. That was just get to the p-value and stop. Is that good? Questions on that one? All right, on we go. Number 5. 10 different, let's hold on one second. On we go. 10 different families are tested for the number of gallons of water a day they use before and after viewing a conservation video. Construct a 90% confidence for the mean of the differences. Okay, so what kind of test is that one?
Matched.
Are they matched?
Before and after.
Good. Did you notice those words? Yeah. I went back over here. Yeah, good eye. Yeah, if you come back to the 2 dependent matched pairs, I gave an example. I said before, after. Yeah, if it says before and after, or like a couple, male, female, husband, wife, actor, actress, all those kind of cases are matched pairs, aren't they? So, yeah, that's right. Those are matched pairs. So that means we're going to put the data in L1 and L2 and go L1 minus L2 stored in L3 and then do t-test. Let's go do that. So where are we at? This one? So yeah, these are matched. Matched pairs. Now you want to be careful though. I don't want you to think just because they have the same number of entries, it's always matched pairs. But it's because they say before, after, So in other words, this is the same family. You get the idea? That's the same family before and after watching the conservation video.
The other type says independent, simple, random samples.
Yeah, right. These aren't independent, are they? Like, tell me about that first family. How did the conservation video strike them? Were they deeply impacted by the conservation video?
Not the first time around.
Right. See what the data's saying? Is the data talking to you? Can you hear the music? Does the data have meaning for you? Right? Before watching the conservation video, that family used 33 gallons of water a day. And then after they watched the video about conserving water, the next day they used 34 gallons. They thought, yeah, we better up it before it all runs out. They were deeply struck. All right, so so that's the idea, right? So, but it's family by family. This is a different family. They were more struck by the video, etc., right? Get the idea? That's why they're matched. Does that make sense? Those 10 numbers on the top, or however many numbers on the top, are not totally independent from the numbers on the bottom, are they? They're matched up. They're connected. They're the same family. Family by family by family as you go across, right? All right. That's the logic behind it. Okay, so what is HO? What is H1? Oh, I should have put that in for you. Yeah, let me do that, guys. Back here, I think it might help you. HO is going to be mu1 equal mu2, and H1 is going to be mu1 greater, less, or not equal to mu2. If you want to write that in, you might want to. That'll help you. That's how we're always doing the two dependent matched pairs. It's just like the independent. The HO and the H1 look the same. Okay. So yes, if you missed that, if that was too fast, it's an identical copy from step 2 on the notes. All right, so it's right, and I'll write it right here. Mu1 equals mu2. Mu1, it's either going to be greater, less, or not equal to mu2. So which one is it? How do we know which one it is?
After is less than.
We don't even. What am I even doing?
Yeah, we don't need it.
They were doing a confidence interval. I better read the words before I start diving in. We're doing a confidence interval, not a hypothesis test. Yeah, confidence interval. My mistake. So we're gonna. Well, how do you do the confidence interval thing? Let's go back to the notes again. I'll think straight here. We're either gonna do t-test or t-interval. Oh, we got to put the data in L1 and L2. I keep forgetting. So let's put the data in L1, L2, and do this L1 minus L2 stored in L3 thing. So that's what we got to do. So this is L1. So let me get rid of this here. So this is L1. This is L2. Put the data in there. Stuff in L1 and L2, and then you've got to go second quit because you got to quit the table entry thing. The quit button is right at the top above the mode, right next to the second button. Quit that, and then you've got to go L1 minus L2. Stored, the store button is on the left side above the on, into L3, and hit enter, right? Storing the differences into L3. And now they're into L3, and then we can go do the confidence interval. And it's just going to be a T interval, isn't it? If you look back on the notes, it just says do a T interval, which is down on number 8, and choose data, right? This time we're choosing data because we just put a bunch of data in. And then that's going to ask you for the list. And that's, what's the list? L3, because that's where our data is now. It's the differences which are in L3. Frequency is always 1. And the sea level, what confidence on 0.90, 0.9. And calculate. So I'm getting an answer which says 1.76 to 7.84. It's that one rounded to one place anyway. There we go. Is that good?
Going over the final on Tuesday next week, or?
All right. So next one. We can get another one done. Next table below shows the weights of 7 subjects before and after following a particular diet for 2 months. Oh, that's going to be the same thing, isn't it? Yes. Before and after. I'm just going to skip on. That's okay. Let's go down now. Let's do number 7. How about the bear thing? So you're measuring bears' chests and their weights, and they're asking us if there's a connection between the bear's chests and weights. So it says somewhere, doesn't it? Guess it doesn't say much. Oh, regression equation. Yeah, it says find the regression equation. Right there. So as soon as you see those words, you go, oh, okay, that'll help. Go back go back to the exam notes and say regression. Where does it say regression stuff? Here and here. Remember, 7 you're supposed to cross out and not use. When I made that, it only works on my calculator and some like mine, but not all of them. So just do 8 and 9. It'll take care of everything. So to find the regression stuff, do 8 and 9. So basically, we're going to go to linear regression t-test. That's what both 8 and 9 say. Go to the linear regression t-test. Put the data in L1 and L2, and go to the linear regression t-test. And then right away, we're going to need to look at the p-value. Remember these? Where we examine the p-value. And if the p-value is low, then we use our regression, the linear equation. If it's high, we don't. Let's carry it out. Okay, so we put this is L1, L2. Put the data in there. Put the data in L1 and L2. And then what you do is hit linear regression t-test. So that's under the stats. It's near the bottom. You can roll up from go top and go up. Find it quicker. Linear regression t-test. And now, if you notice, let me go back to the exam 4 notes. It says not equals. Do you see that? I'm putting it right on the notes for you. Choose the not equals option on the linear regression t-test. So let's do that. We'll choose not equals. And calculate. And I'm getting a p-value 0.01. So what does that mean according to the exam 4 notes?
Less than significant.
Yeah, so it says right here, if your p-value is less than 0.05, then there's strong evidence of a linear relationship, correlation. So use the equation, plug in x to find y. Is that making sense? So there's strong evidence that the dots, you can see the dots if you want to hit, zoom in 9. We don't need to. They must be pretty tight line. They must be making a pretty good line. So that means these two variables do have a linear connection, a linear relationship. So yes, let's use the linear equation. That's what it's saying. So let's go back. So that means they are linear. There is a linear correlation between L1 and L2, the bear's chest size and his weight. There's a linear relationship. The bigger chest, bigger weight, lower chest, lower weight. Pretty stable for the bears. So then we use the equation. So use y equals a plus bx. It'll tell you the a. I'm getting minus 246 point. I'll just go 4. That's enough accuracy. You don't need to do all the digits. I did on the homework. I had you use a bunch, but on the exam, see how I rounded the answers? Just using a couple will be fine. Making things a little simpler in the exam. 9799x. And then I'm going to plug in the x. Plug in x equals what? 45 inches. So right there, put in the 45 for x. They're saying if a bear, remember x is the bear's chest and y is the weight. They're saying if a bear's chest is 45 inches around, what do we think the bear's weight is going to be? We can use that to predict the bear's weight because these two variables have a very linear correlation, connection. So what does y come out to be? Just type this out on your calculator. And we'll see. I'm getting 292.6, so that rounds to 293. And there it is. That bear, we're predicting, weighs 293 pounds. So there'll be one of these. Linear regression, predict the thing, questions on the exam next week. And it may or may not, I don't even know. I don't remember. I have several versions. The p-value might be higher than, now what if this p-value, so the one you get next week, might have a p-value higher than 0.5, right? Because this p-value was less than 0.05, that means use the equation. But what if p was something like 0.07, which is greater than 0.05? What would we have done in that case? Yeah, so I put it on the exam 4 notes, back over here, exactly. I said if it's greater than 0.05, then there's not strong evidence of a linear correlation. Those dots are not connected linearly. The variables do not have a linear relationship, so don't use the equation. It's garbage. It's just make-believe, fairy tale equation. It doesn't really describe how the two variables relate to each other. You instead do this, stat calc 1var L2 and find the x bar, the average. In other words, if the two variables are not related in a linear relationship, all you can do is give the average. And so you would just do that, and that would give the average, bare weight, and that would be your prediction. Just, well, you want a prediction on the weight? I'll just give you the average weight. That's what that would have been. That might be what happens on the exam next week. I don't know. It's going to be one or the other. I have some versions with one, some versions with the other on that. We don't have time for another one, so we're going to have to stop there.